Hello, I am going to demonstrate the experiment performed using HPTLC. Our aim is to measure the unknown concentrations of benzophenone and benzhydrol in a mixture using high performance thin layer chromatography. So before that, I'll introduce what is chromatography. So chromatography is one of the technique that is used for separating components of mixtures based on the distribution of the concerned components between a mobile phase and a stationary phase. So the mobile phase can be a moving fluid, while a stationary phase can be a liquid or a solid. So depending on their respective affinities. So the various types of chromatography are there. So they are gas chromatography, liquid chromatography, ion exchange chromatography, paper chromatography, and thin layer chromatography. So thin layer chromatography, it is used to separate non-volatile components from a volatile ones, and it is also used for monitoring the chemical reactions, identifying the various components present in the reactions, and it also determine the purity of products. So the high performance thin layer chromatography, it is an advanced and enhanced version of thin layer chromatography, which includes more automation and allows higher resolution for the analysis. Now I'll talk various advantages of HPTLC over TLC. So first is the auto sample max is better than TLC since it overcomes the manual error. It provides high resolving power. It reduces solvent consumption, and it utilizes ultraviolet visible or fluorescence detectors. It enables simultaneous analysis of multiple compounds, and it's highly precise. Then I'll talk about the various advantages of HPTLC over HPLC. So in HPTLC, the preparation of sample is simple compared to HPLC, and here consumption of solvents per sample is very low, and maintenance costs are also very low, and there is no effect of turbidity of sample on analysis in HPTLC, and the whole spectrum can be seen in HPTLC, and it is a highly flexibility in the different steps such as the selection of mobile phases, stationary phases, and developing techniques. So and the in HPTLC the percotted plates are available in low cost, and it provides better analytical accuracy and precision since sampling and standard can be processed simultaneously. Now I'll talk about the theory behind the chromatography. So chromatography uses a mobile phase and a stationary phase, with the mobile phase rising off the stationary phase due to capillary action. Since the component of the mixture has different affinities towards the mobile and stationary phases, different distances will be traveled by them. In experiments, stationary phase used in the TLC plate is the silica coated on aluminum sheet, while the mobile phase is a solvent which can vary according to the separation requirements. A nonpolar organic component will have more affinity towards the acetone than silica. So in that case, when a mixture is brought in contact with silica and acetone, the distance traveled by the nonpolar organic component will be more due to greater affinity towards acetone. By contrast, the polar component having relatively greater affinity towards silica will get adsorbed on the same and remain almost stationary. So we'll define a term called partition coefficient, which is the ratio of the concentration of the analyte in a stationary phase to the mobile phase. So a higher partition coefficient indicates that the mixture has more affinity towards the stationary phase, and it will migrate relatively slowly. Similarly, we will define another term called retention factor. and it is the ratio of the distance traveled by the solute to the distance traveled by the solvent front. So in an experiment, the solvent to be used is governed by the retention factor of the solvent for the concerned solute. And another thing is the wide difference in the retention factor values of a different solute ensure that they can be easily separated. The experimental apparatus that are required for this HPTLC experiment are TLC plate, which is a silica coated over aluminum sheet, an applicator, a glass developing chamber, a TLC UV scanner, micro syringe, beakers, pipette, and sampling bottles. The reagents and chemical used are benzophenone, benzhydrol, methanol, hexane, and toluene. First, we will prepare two different standard solutions. The first one is the benzhydrol, and the second one is benzophenone. So here we have added the 5.94 milligram of benzophenone in 50 ml of methanol. So likely we have also added 98.99 milligram of benzophenone in 50 ml of methanol. So we have prepared these two standard solutions in methanol. So then we will take a we'll prepare a unknown concentration from these two standard solution. So here we don't know the concentration of the prepared solution. We will just randomly take and we will add. Then we rinse with methanol. Then we will take another standard solution of unknown volume. Then we will mix these two solutions, standard solution, and we will prepare a solution of unknown concentration. So this unknown concentration solution is prepared from the benzhydrol and the benzophenone standard solutions. Then we will fill this unknown solution. So first we will fill this standard solution benzhydrol with syringe. Make sure that there is no bubble inside the syringe, so we have to remove these bubbles. Then we will just put this inside this applicator, inside the applicator. Just to put a tissue paper below it to ensure that the solvent is there inside this syringe. Then we have prepared a plate of dimensions of its length is 20 centimeter and this width is 10 centimeter. So then we will put and we have mounted 7 centimeter from the bottom, so that up to this height the solvent has to move. Now we are putting this plate in the applicator. here you can see 15 bands are there. So we are going to prepare 15 bands. 6 bands are from benzophenone, another 6 are from benzhydrol, and another 3 are from samples. So now we are going to start. So first for this we have to press this gas and then run. So here you can see the bands are preparing over this plate. So likely we have to prepare 15 bands. The first 6 are from the standard solution benzophenone, the second 6 are from the standard solution benzhydrol, and the last 3 are from the sample. So the first 6 they are the volume are like that. We have prepared first 2 microliter. First band is 2 microliter. Second band is 2 microliter duplicate, and the rest are 4 microliter, 6 microliter, 8 microliter, and 10 microliter. Similarly, we have also prepared the bands of different volumes from benzhydrol, and finally the last 3 bands are from the sample of unknown concentration. They are as 4 microliter, 6 microliter, and 8 microliter. We will prepare a developing solvent from this N-hexane and a toluene in the ratio 3:10 for this HPTLC experiment. So we have we will prepare a 20 ml of developing solvent inside the glass developing chamber. So we have taken a 4.26 ml of N-hexane and 15.38 ml of toluene. So we have mixed these two solvents inside the glass developing chamber, and we have shaken it thoroughly so that these two solvents will mix thoroughly inside this glass developing chamber. Then we will keep it for 20 minutes. Then after 20 minutes we will put this plate into that glass developing chamber. So the bands have prepared over this plate. Now we are going to dip this plate into this glass chamber after 20 minutes of preparing of solvent. So we will keep it at an angle at a slanting angle. Now you can see the solvent is rising up inside the stationary phase. So we will wait till the solvent has come to up to the mark. So after that we will remove this plate and we will dry it. Now you can see the solvent has reached the marked point. So it has moved 7 centimeter from the bottom. Now we have to remove this plate from this glass developing chamber. So we should not disturb this part, the solvent traveled part. So now we will dry this solvent using this dryer. We have to dry it for a certain time so that all the solvent has evaporated. So now you can see the solvent has totally evaporated. So now we will see the bands formed in this plate. So we will see it inside the 366 nanometer UV lamp. So you have to switch it on, this UV lamp. So now you can see the bands are formed. So the bands, you can see the bands, first 6 are from this benzophenone and the next 6 are from benzhydrol and the last 3 are from samples. So where this benzophenone and benzhydrol in this unknown concentration sample, it is separated into two bands. So here you can see the first 6 benzophenone has traveled a greater distance compared to benzhydrol, because the benzophenone is less polar than benzhydrol. So the benzhydrol stick more to the silica, that's why it's travel lesser distance compared to benzophenone. We are going to scan the bands found in the silica plate using this CAMAG TLC scanner. So at 254 nanometer wavelength. So we will switch on this scanner, UV scanner. So you can see it's switched on. So now we will it needs some time to start. Yeah, now it's ready. So now we put our plate inside the scanner. So now the plate is ready to scan. So we have to operate this scanning procedure using a Vision Cat software. So we have to open this software, this Vision Cat software we have to open. So it has opened this software. So before scanning we have to prepare our various steps. So this HPTLC steps, it includes application and this development and detection. So first we have to enter various parameters in the application and in the glass development chamber and for the detection. So we'll see what are the parameters we are going to enter. So here we have to enter these parameters related to plate, that means the type of stationary phase and this plate dimensions, and this here this application position, the first track position, track distance, and all those things are mentioned in the manuals. So we have to enter these parameters, then we have to press OK. Then after that we are doing this manual application, so nothing has to be there in. Then we will go to the glass development chamber. So in the glass development chamber we have to put 20:10 for this plate, and the mobile phase we will choose is the N hexane and toluene in the 3:10 ratio, and we have to press OK. Then we have to go to the scanning section. So here we have to choose the single wavelength lambda, the scanner type, and the optimization for resolution, and the slit we have to use 6 into 0.45 mm with a scanning speed of 20 mm per second, and here we have to choose the deuterium lamp, and the wavelength is at 254. We are scanning 254 nanometer. Then we have to press OK. Then after this it is ready to scan, we have to press continue. So once it is pressed continue, see all those bands it will scan one by one, and the corresponding peaks will be generated. After scanning, corresponding peak will be generated. And another thing I forgot to say, that we have to enter this vial ID, and some descriptions also we have to enter. So here I have entered all those descriptions, like first 6 bands corresponds to benzophenone, and the next 6 bands corresponds to benzhydrol, and the last 3 bands are from samples. So we have mentioned the volume of the bands, and first 6 standard we have entered, we have given a single vial ID BP1. BP stands for benzophenone, and the next for the second standard sample we have given a vial ID BP BH benzhydrol, and the last SA stands for sample. So now we'll go to the, we'll see the data. So you can see this, all those peaks has come after scanning the bands. So here the first one has lower retention factor, and the second one has higher retention factor. Two peaks has come. So this higher retention factor corresponds to benzophenone because it has traveled a larger distance, while this one corresponds to benzhydrol of lower retention factor, while the sample has both the bands. So accordingly we have, you can see there are 15 tracks are there. So first 6 are benzophenone, next 6 are benzhydrol, and last 3 are from samples. Next we'll move to this evaluation section. So this evaluation section involves so many steps. First we have to define the concentration of standard. So here we have defined the concentration of benzophenone used, that is 118.8 microgram per ml. We have converted milligram into microgram per ml. Since we have added 5.94 milligram of benzophenone in 50 ml of methanol, so we have converted accordingly. Similarly for benzhydrol also we have got a concentration of 1.979 milligram per ml. So after entering this concentration details, we have to go to this integration section. So this integration section, we have first calculated this standard for this benzophenone, the standard solution for benzophenone, and the benzophenone present in this unknown concentration sample. So you can see various peaks has come. So we have chosen our window to this peak, and after that we have to move to this substance assignment section. So in this substance assignment section we have to bring this window to near to these peaks, and you have to adjust so that, and then we have to press on this eye we have to press on, then we will get the corresponding this calibration plots. So here you can see this is the linear plot for the standard sample. So this green plus sign are from standard, while this blue cross sign are from the sample. You can see 3 samples are there, or 3 lines has come. So here this correlation coefficient is coming around 0.997, which is quite better. That means the fitting is quite better. So after that we will get this result. So you can see this, we are getting the concentration for this 3 from these 3 bands, it will last 3 bands, 13, 14 and 15 bands. So this concentration of this unknown sample is coming nearly same. So next we will evaluate for benzhydrol. So we have to go for another evaluation. So in this evaluation we will also in the similar manner we have to enter this concentration of benzhydrol and benzophenone. Then we have to go to this integration section. So here you can see this benzophenone parts are off. This track corresponds to benzophenone are off, while the tracks corresponds to benzhydrol are on, and the tracks corresponds to the sample are on. Then we have to integrate, we have to bring this blue lines near to this required peak, and we have to integrate. Then after that we have to go to substance assignment. So here we have to bring this cursor near to this peak and we have to adjust. Then after that we have to press this I button so that it is on. Then we have to move to calibration section. Here you can see this green cross are from the standard sample, while is this blue cross are from the sample. Here you can see instead of 3 cross only 2 cross are there, while the another for the another sample, it is moved out of this line. So we are getting the correlation factor of 0.999, which is quite good. Then if we go to the result, then we are getting only for these two sample, that is corresponds to SA2 and SA3. That means for 14 and 15 tracks, that is 6 microliter and 8 microliter. Here 4 microliter sample has not come because its concentration is low, so that this it is lying the outside of this straight line. So we have to decide the concentration in such a way that the sample has to lie within this straight line. So here you can see this concentration of this unknown sample are coming nearly are matching together, coming around same. So in this, in this way, we can calculate the concentration of an unknown concentration sample using this HPTLC with a better accuracy.